So we'll deal with motion of fluids or fluids in motion. And mainly we will deal with liquids in motion, because we will deal with the ideal fluid. What is an ideal fluid? It has got two characteristics. One, it should be incompressible. Incompressible, that means its density is constant. Density rho is constant. That is an incompressible fluid. And in case of gas, it cannot be incompressible. You cannot model the equations of motion of a gas with an incompressible sort of model. It's impossible. So we will deal with actually liquids in motion, because ideal fluid means it has to be liquid, and it should be inviscid. That means, so inviscid or non-viscous. That means there is no viscosity, no viscosity or fluid friction. Viscosity is the friction force between fluid layers themselves and the solids. Viscosity is friction between the layers of fluid. That means when the say we divide the fluid into layers, and suppose the bottom layer is fixed and the top layer moves with a certain speed v, so it will apply a force on the layer at the bottom, right? Say this red layer is acted upon by a friction force F, and the top layer that will encounter a friction F towards the left. That means it is friction between layers of the fluid. Viscosity, we will learn in details about viscosity in a different topic. Okay, so ideal fluid is a fluid which is incompressible and also inviscid or non-viscous. Next we will learn about steady and unsteady flow. So steady means time independent. Steady means time independent. Steady flow means in steady flow. In case of steady flow, the flow parameters, suppose for example velocity of the fluid at a certain point. Velocity of the fluid at a certain point in space, or a certain point in a fluid in motion, remains constant with time. That is steady flow. Else it is unsteady flow. Obviously you know what is an unsteady flow. Whichever is not steady flow is unsteady flow. Now, a steady flow does not mean that the acceleration of the liquid particle is zero. No, it's not that. It is not that. See, what is mentioned in case of steady flow? That flow parameter, example, velocity of the fluid at a certain point remains constant with time. It is not that of the same fluid particle. Suppose I tell you a pipe. So this is a pipe, and And you know that if the diameter of the pipe, see at the points where the diameter of the pipe is lesser, fluid velocity is more there. We will also learn in the equation of continuity. If you have a water sprinkler, right? So if you make the opening of lesser cross section, fluid will flow with a higher speed. So like this, right? So obviously, if you track a fluid particle like this, say this fluid particle, I draw any fluid particle, this yellow dot is a fluid particle. Now at a certain time this fluid particle is here, and after a certain time the fluid particle moves somewhere there to the right. So is the velocity of the fluid particle same? No, it is not at all same. So this is low velocity in this region, low velocity, and where the cross section is smaller you have high velocity. So the fluid particle, its velocity changes as it moves along. See, this is the path of the fluid particle. Right? I'll show by the pointer. See, the same fluid particles moves here. Its velocity changes. But what happens? The see, once this fluid particle moves to this position to the right, it is replaced by one more fluid particle, right? Then also its velocity remains same. That means suppose the velocity at this point is v1 and velocity at this point is v2. So at a particular point in space, that means at this point, at this position, velocity of all fluid particles passing through this point, or fluid particles passing through, is v1. Got the point? Velocity of all particles passing through that point is v1. Or you can say that suppose v is a function of what? If you say the coordinates x, y, z and t time, right? In steady flow, what happens? V is a function of what? X, y, z only. It's not a function of time, right? V means velocity of a fluid particle. So this is the situation at time t. We are discussing steady flow. What is meant by steady flow? And this is time t plus delta t. Delta t is the time interval. So now this is the yellow fluid particle and there is the green fluid particle. Now the yellow fluid particle, suppose here the yellow fluid particle is having velocity v1, and suppose you have one more a red fluid particle here which is having a velocity v2. Now after time dt, what happens? The yellow fluid particle reaches here and the red fluid particle goes down there. Red fluid particle goes there and the green fluid particle gets here. Now what is the velocity of the green fluid particle now? That's v1. What is the velocity of the yellow fluid particle now? It's v2. So that means at a certain point, say this is a point having coordinate, say a point P having coordinates x, y and z. So point P, at point P, x, y, z, all fluid particles all fluid particles uh, passing through this point P will have velocities uh, v1, right? So that will not change with time. That won't change with time. Got the point? That is known as steady flow. This is known as steady flow, right? Suppose this v1 is 10 and v2 is 20. So it remains same, 10 and this 20. Because this is the same point P, X, Y, Z. Not the same fluid particle, right? Different fluid particles pass through the point P at different times. But the velocity of the fluid particle at point P remains unchanged with time. That is the meaning of steady flow. Now, steady flow is also known as streamlined flow. Steady flow is also known as streamlined flow. Now, I'll discuss what is meant by streamline. Now, streamline is an imaginary line along fluid flow. Imaginary line along fluid flow, so that tangent to it at a point shows the velocity vector or velocity of the fluid passing through that point. So that is known as a streamline. See, don't confuse streamline with locus, right? It's not same. Streamline. But for steady flow, it is same as locus of a fluid particle. See, in a steady flow, the streamlines are fixed. Say this bent pipe, I'll tell you. For this bent pipe, these red lines are the streamlines I'll draw. And they are given some directions also. Else you never know which way the liquid flows. So at point, say I mark point A, point B, or say point C. These are on the same streamline, right? So at point A, velocity vector is along VA. Okay, we cannot find out the magnitude, but we can predict the direction of fluid particle. So at B, velocity vector of the fluid particle is VB, tangent to the streamline at that point. At C, velocity of the fluid particle is VC, tangent to the streamline at that point. Say another point, say D here. So velocity vector of the fluid at point D is Vd, tangent to the streamline at point D. So that is the concept of a streamline. And you know that two streamlines can never intersect, right? Why cannot they intersect? Two streamline can never intersect. Because if two streamlines intersect, that means at a point you cannot have two velocity vectors, right? So these two streamlines intersect. That means they at the intersection point you have two tangents, so two velocity vectors. That is not possible. So that is why two streamlines can never intersect each other. And also more closely packed the streamlines are, more is the velocity at that region. That you can see in that diagram, right? See here the streamlines are more closely packed towards the right side, and They are not so closely packed in the left side. So velocity of the liquid is more in the right side when the streamlines are more closely packed together. Suppose there are two pipes like this and liquid flows through two pipes. Liquid comes in from this pipe, so the streamlines will take a shape like this. They will never intersect, but they will take a shape like this. Now there may be pipes like this. Okay, say liquid flowing from this direction and this direction. They are also streamlines, do not intersect. They take a path somewhat like this. So here we will learn about the equation of continuity for an incompressible fluid. So we'll take that same tapered pipe like this. Now, so these are the streamlines. By the way, I forgot to tell you one thing, that a collection of streamlines is known as a stream tube or a tube of flow. However, okay, so that's these are the streamlines. Now we take a certain section of the fluid. Say we take a section. Say this is AA and this is section BB. Right now, say at the section AA. So at section AA, speed of fluid is V1, and at section BB, speed of fluid is V2. Now, say in a small time dt, in a small time dt, so AA moves to A dash A dash by a distance how much? V1 dt, and BB moves to B dash B dash by a distance V2 dt. So let's move AA to A dash A dash and BB to B dash B dash, and the distances moved are, that is V1 dt and BB dash is V2 dt. And say A1 and A2, say A1 and A2 be cross sections at AA and BB, at sections AA and section BB. So what is the volume of liquid that flows through in the section AA? This volume of liquid which flows through in section AA, and volume of the liquid that flows through in section BB. So this shaded volume is equal to A1 V1 dt, while that shaded volume to the right side, that volume is equal to A2 V2 times dt, right? So cross section into distance is the volume flow. So the volume inflow and the volume outflow that has to be same because the fluid is incompressible, right? So as the fluid is incompressible, we can say that fluid is incompressible. Therefore, we can write volume is equal to volume out. Volume in means A1 V1 dt is equal to volume out A2 V2 dt. That is A1 V1 is equal to A2 V2. So equation of continuity is a way of writing conservation of mass. For the incompressible fluid, it is conservation of volume because the density remains constant in this case. By the way, you should know that A into V, cross section into speed, is the volume flow rate. Volume flow rate of liquid through a pipe is given by A into V. See, if the cross section is A, cross section of the pipe is A, and speed of the liquid is V, then the volume flow rate is A into V. Why? Because in time dt, say consider a fluid particle. Consider this, or say I'll explain in a better way. Consider your see toothpaste, right? This is the toothpaste, opening of the toothpaste. Let's see how much toothpaste flows in time t. So there the toothpaste is coming out, right? Now this is time. Uh, Now this is time t equal to 0. Just the toothpaste is starting to come out. T equal to 0. Now and say this opening has a cross section A, right? So in time t, how much toothpaste will flow? Let's see. So in time t we have considered, right? In time t, this much toothpaste will flow. This dotted part. So now this was at time t equal to 0. Now this is at time t equal to t, right? So the toothpaste moves how much distance? The tube, I mean this paste moves a distance v into t. So how much volume flows? How much volume? So in this dotted portion, how much volume? Volume is equal to A cross section into V into T, cross section into distance, because the toothpaste is the shape of a cylinder approximately. So A V into T. So now divide the volume by time. Time is T. So what you get? A V. So A into V is what? The volume flow rate. So so in the same way, if liquid flows in a pipe of cross section A with a speed V, then the volume flow rate of fluid is equal to A times V. If volume flow rate is A into V, then if rho is density, so rho A into V is the mass flow rate. So the equation of continuity is not only limited to this one pipe, right? So you have a pipe like this. So at a point here, the cross section is a1 and the speed is v1, and in a different point cross section is a2, speed is v2, and there cross section is a3 and the speed is v3. So we can choose a region. Here, this region, say this marked by red, this region. So in this region the volume remains constant with time, so volume flow in is equal to volume flow out. So what is the total volume flow in? So that is a1 v1 plus a2 v2. Total volume in is equal to volume out equal to a3 v3. So this is the equation of continuity in this case. So it is valid for multiple streams, right? Multiple streams, maybe 3 or 4 junctions, like that. It's also valid in that case also. So main thing what we have done, we have applied conservation of mass, or rather conservation of volume. We have chosen a certain volume, a certain region of space inside the pipe, and its volume remains constant with time. So volume in this region is equal to volume out. So the most important equation of fluid dynamics is the Bernoulli equation. The Bernoulli equation is valid for steady flow of an ideal fluid. What is an ideal fluid? We have discussed before. It has no viscosity and its density is constant. That is an non-viscous and incompressible. If both these qualities are satisfied, then it is an ideal fluid. So in this Bernoulli's equation, let me tell you the Bernoulli's equation first. So let us consider a streamline. So this red one is a streamline, and consider any 2 points on this streamline. So point 1 and point 2 on the streamline, right? So from this Bernoulli's equation, the points 1 and 2, points 1 and 2 are on a streamline, and at 1 velocity is v1 and pressure is p1. At 2 velocity is v2 and pressure is p2. And from a certain datum level or reference level, say at say z1 and z2, z1 and z2 are heights of 1 and 2 from a certain reference level, then the Bernoulli's equation Bernoulli equation says that P1 plus half rho V1 square plus rho G Z1 is equal to P2 plus half rho V2 square plus rho G Z2. This is the Bernoulli's equation. Still I have not proved. I will prove it shortly. Where rho is the density. Rho is the density of the liquid. So that is the Bernoulli's equation. Or you can say that P plus half rho V square plus rho Gz is equal to constant. Obviously for points on a streamline. Now we will prove this Bernoulli equation. We will consider any two points along the streamline and very close points, and the distance will be ds. ds is a very small distance, and say consider a very small element, a very small cylinder made of the liquid itself, like this. And suppose the cross section is dA. It's a small, so the cross section is also small. So let the cross section be dA, and let this angle be theta, right? Let the angle at this point, angle with the horizontal be theta. So what about the height? What about the height? The height is dz, right? Dz is equal to ds sine theta. So isn't it true? Dz is equal to ds times sine theta. Now we have chosen this small, very small cylinder. So this small cylinder is having area dA, and the pressure at this end is P, and the pressure at that end is P plus dP. It varies along the streamline. So P plus dP. So the force is P dA, and there P plus dP times dA. And what about the weight of the fluid particle? Weight of the fluid particle is ds dA volume into rho g, and the component of the weight parallel to the streamline, this is the component of the weight along the streamline. It is like the inclined plane, right? So there is one more component, we are not much interested in that component. So like in the inclined plane you have that mg sine theta. So that way this is ds dA rho g times sine theta. Look at this figure, I think is quite clear. The force due to pressure and the component of the weight. There is one more component of the weight, just I'm drawing it, but regarding calculation we are not interested in that. So the equation of motion will be similar to that of a particle climbing up the inclined plane. So apply Newton's law for the particle, for the small fluid particle of area dA, that means cross section area dA, and length ds is what will be Newton's law. So the force P dA minus P plus dP times dA minus ds dA rho g times sine theta, net force, equal to mass times acceleration. What is the mass? Rho ds into dA, mass of the fluid particle, and the acceleration you can write v dv ds. So this v dv ds, this term is the acceleration of the fluid particle. So now let's rearrange the terms. So P dA minus P dP, so there, so let's cancel all the dAs, right? So you get minus dP minus rho g ds sine theta, we have to do something about that also, is equal to rho dA has gone, right? And ds will also cancel. So rho v dv, right? Because you have a ds here and you have a ds here, so those two will cancel, and dA is already being cancelled. So therefore, what you get is dp plus rho g. See, ds sin theta is dz. We have calculated that, plus rho v dv is equal to 0. Now we'll integrate, because we have chosen here 2 points on the streamline, on the same streamline as that, and same streamline on which we have considered the small fluid particles, points 1 and 2. So we'll integrate here. Integration of dp plus integration of rho g dz plus integration of rho v dv. So that's equal to 0. So integration of, now we'll put the limits. So the limits will be from p1 to p2. We integrate from points 1 to 2. So p1 to p2. Now rho, as the density is constant, rho will come outside the integration sign. So however, here you have z1 to z2, and here you have v1 to v2. So therefore you have p2 minus p1 plus rho g, z2 minus z1 plus half rho v2 square minus v1 square is equal to 0, implies p1 plus half rho v1 square plus rho g z1 is equal to p2 plus half rho v2 square plus rho g z2. So this is the Bernoulli equation.